All right, metal alloys and crystals. The point they're trying to make is that they are going to go with lattices and substances that are not present in the molecular form, that are present in bigger structures. They are going to consider those over here. Okay, so that's why the terms metals, alloys, and crystals. Okay, if you look at it, they have given the key definition of all four different type of solid structures that we get. Number one, metallic lattice that we get from metallic bonding. It's actually a lattice of positive ions in a sea of delocalized electrons. Metals form this kind of structure. The next one is giant ionic lattice. As the name suggests, it comes out as a product of ionic bonding. It's a lattice of alternating positive and negative ions. And actually, this is a combination of a metal and a non-metal both. Next up is giant molecular lattice. A giant molecular lattice or macromolecule. The word macro itself means huge or gigantic. So we still are keeping that this specific topic for the next pages. So yeah, after a couple of pages, we're going to get started with this one. And they also make the lattice. They are made up of covalent bonding. As the name suggests, the word molecular itself comes from covalent bonding. So it is made up of nonmetals only. The last one are simpler molecular substances. So since they're molecules, they are simple ones, they're small, they're made up of very easily countable number of atoms. So actually they're not in lattice, they're in a structure where they're held together by weak forces of attraction, which we usually overcome with a little bit amount of heat. That's why their melting and boiling points were low. That's why they were usually gases or liquids at room temperature. But since they're talking about the solid ones, we're going to consider the solid one in this portion. All right. So they are going to be in the form of a somewhat, we can call it a lattice, but again, very weak forces of attraction are there. Okay. So let's move on and let's define all four of these one by one in detail. So moving on, we're going to start with metal crystals. Now, this is something that I've explained really in a lot of detail during the metallic bonding. So I'm going to just quickly skim through the entire portion because we have already understood it, but I want to make sure that I don't skip a point. So I will discuss each and every point there is in there. Okay, so it's a regular packing, metal ions. These are all positive ions. They're surrounded by a sea of mobile electrons, which we usually call delocalized electrons. Packing is as close as possible because of the electrostatic forces of attraction. Positive ions has a positive charge, delocalized electrons have a negative charge. That's why the packing is closed. They usually have a high density, all right? In some metals, the ions are less closely packed, but those are only just alkali metals. That's why they have low densities and they float on water. But apart from that, what usually we talk about metallic crystals, we talk about the transition metals, which are hard, which are strong, which have high density, high melting and boiling points. Now their structures are based on layers. If we apply some force without breaking the structures, the layers are flexible enough to be able to roll on one another. So whenever we beat them or roll them, they're converted into sheets in the properties known as malleability. Metals are more malleable when we convert them or into different structures when they're hot. So steel is rolled when it's hot. They can also be stretched or pulled or drawn into wires. The property is known as ductility. The diagrams on the top of the page give us a very good idea. So whenever we apply force on a set of layers, the layers can simply slide over one another. Metallic bonds remain because the delocalized electrons outside the structure form new bonds and keep the whole packing in place. So metals do not break into smaller pieces that simply change their shape. Make sense?
Yes, sir.
Good. Now, the movement of relocalized electrons mean that they conduct electricity in a very good way. Copper is a particularly good conductor, and we use copper for domestic wiring. However, for overhead power lines, aluminum is used because it's lighter. Aluminum is not strong enough, so we use a steel core. Sometimes metals have like a grain-based structure, and there are some grain boundaries. This was an old part. This is not a part of the new book anymore. So you can simply skip these grain boundaries and grain stuff, this one and this one. They're not a part of the new course. All right. So I'm going to skip all of this. Okay.
Okay, sir.
So uh, just so next up is alloys. Alloys is actually made with a combination of metal with other metals. Sometimes we may add non-metals. The process is really simple. We heat them, we melt them, they're converted into liquids, we mix them thoroughly, we allow them to cool, they form a solid very quickly, and that's how we make alloys. Now, alloys are actually made up of a different combinations. Now, whatever we're going to add to the basic metal, that's going to give it, impart to it specific properties. And particular properties is something that we need to understand. Now, in this entire table, you're supposed to do this entire table except these parts. You're not supposed to go with these parts. You're not supposed to remember the percentages. Rest, you may remember that brass is made up of copper and zinc. Now, it is harder than pure copper and it has a golden color. So zinc gives it a little bit of a color, and zinc also gives copper some hardness because zinc ions are usually bigger. Zinc ions, or we can say zinc atoms, are bigger than copper atoms, so it gives it some hardness. We're going to explain hardness in the diagram on the left. We're going to do it a little later. Let's continue with the table. Bronze is made up of copper and tin. Now, tin gives copper some hardness. Again, the size of atoms is different, because of which it becomes harder. Now, the next up is mild steel. We're going to study in much detail in chapter number 9, but for now, iron is usually mixed with carbon. A little bit of carbon can give strength and hardness to pure iron. Stainless steel, the steel that usually does not get any stains, hence the name stainless, actually contains nickel and chromium. Now, nickel gives it hardness, and chromium gives it the property to resist rust. So it does not rust as well as it's hardened in purer iron. So both the elements play their own part. Try to keep that in mind. If it's possible for you, so do mention this is because of nickel and this property is because of chromium. That's a good way to remember it, right? So moving on, solder. It's actually a complete half-half combination, 50-50% combination of tin and lead. It has a lower melting point than either tin or lead, and these are used for many different purposes. For example, brass is used for the places where we have the requirement of a harder something than copper. Bronze is commonly used to make medals. Mild steel is used in the construction of many vehicles. Stainless steel is used in the construction of chemical plants, as well as stainless steel is used to make cutlery. So the spoons and forks in your house are usually made up of stainless steel. And then solder, which is used in soldering iron, where we use it for circuits. Now, there are some examples which are present in between these lines. For example, you can see that aluminum is a very low density metal. It's not strong. So mix it with copper, some other elements such as magnesium, we form duralumin. Duralumin has strength, it is lightweight, so it is usually used for aircraft building. So there are some examples over here. For example, we have cupronickel alloys that are used to make coins. So different examples exist here and there in the book. Whatever example is that, it's usually a mixture of metals and it has specific properties just because two metals have been mixed. Now, since we have been using the term they're harder uh, in case when alloys are there and they're harder in comparison to the parent metals. Why? Because two metals are mixed. For example, in case of brass, we mix copper and zinc. Now, in case of copper and zinc, copper has small sized atoms and we are representing them with gray. Zinc uh, has a larger size atom, so we are representing it in red. So if you can see the diagram, if we apply force on copper, copper is going to slide and become malleable, be converted into sheet really easily. But if you're going to tend to apply the same force, just because there are different sized particles in this entire structure, applying a force actually has some resistance to face. And that resistance is commonly known as hardness of the alloy. I hope that makes sense. Does it?
Yes, sir.
Good, good. So since you understand that how the metal crystals work, let's move on to the second type of crystals, ionic crystals. Now, since I've explained most of these parts already, but we're going to consider a couple of parts for further explanation. So I'm going to go through this one really quickly as well. So in case of ionic crystals, the lattices are positive and negative ions, and they are usually present in alternate arrangement. So much so that the positive faces negative and the negative faces the positive. To further explain it, in sodium chloride, each sodium ion is surrounded by six chloride ions, and in turn, each chloride ion is surrounded by six sodium ions. There are actually equal number of sodium and chloride ions in the charges balanced with one another. How do we put it? Let's suppose sodium ion is in the center, so our chloride ion is going to surround it from top, bottom, right, left, front, and back. That's how each sodium ion is surrounded by six chloride, or each chloride ion is surrounded by six sodium ions. And that's how we get their arrangement. So their actual arrangement of ions depends upon the number of ions involved and their sizes. However, it is important to remember that all ionic compounds are electrically neutral, which means the charges always cancel one another. So if there is one positive, there should be one negative. If there is an ion of a positive 2 charge, luckily there would be two negative ions in order to make sure that we balance the whole compound. That's what this paragraph means. I hope that's clear. Is it?
Yes, sir.
Good. So moving on, ionic crystals are hard, but they are much more brittle than metallic crystals. So what happens if we're going to apply a force on the layers, since metallic crystals, all ions are identical and they are held together by the mobile electrons, so their layers slide over one another. But in ionic crystals, the ions are of different charges. When we push with them with force, the same charges come in front of one another and then they start repelling. Take an idea from this diagram. If we apply a force over here and we actually are able to move certain layers, then they are going to come in front of similar charges. So repulsions, 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 and the entire portion would break from here. That's why they are brittle. Whenever we try to reshape them, they break instead of getting into a different shape. So yeah, ionic crystals are not going to be malleable and they are not going to be ductile either. Moving on, their disruption is brought about by water. Water has a very good property that it can attract charges. Water is able to interact with both positive and negative ions, so much so that a proper system develops. When you look at this diagram, you will immediately understand that the smaller yellow balls are sodium ions, and the larger, somewhat yellowish balls are chloride ions. On the other hand, the red one represents oxygen and the white represents hydrogen. Take a look. When sodium ion is separated, it is surrounded by all oxygen atoms face toward it. And when a chloride ion is surrounded, it is surrounded by all hydrogen atoms face toward it. So the good part is that hydrogen tries to attract the chloride ion and oxygen tries to attract the sodium ion. So they take ion by ion, separated, they break down the whole lattice into many smaller parts, and then they surround those ions. So it's safer to say if I say that sodium ions are all covered by oxygen, and the oxygen are actually bonded to hydrogen. And if I talk about fluoride ions are actually surrounded by hydrogen, and each hydrogen is again bonded to the oxygen atoms in the structure of water, right? So I hope you get the point. Clear enough? So I've drawn them
Yes.
in a symbolized way instead of just ball and stick model. So this is actually the explanation of this diagram in symbolized way. So now you understand that they are able to separate the ions. and the water is then able to surround them. So the ions in the solution are able to move. That's why the solution of ionic compounds are able to carry electric current, which we have discussed before. Ionic compounds can conduct electricity when they're dissolved in water. It's also true that they can conduct electricity when they're melted, because again, when we melt them, we break all the ionic bonds, and the ions are free to move throughout the liquid. And then they can carry the current. And this actually gives you a pretty good idea the arrangement of positive and negative ions in a lattice and how closely and strongly they are packed. You can see that in this diagram. You would notice that the big walls are all chloride ions, so much so that the small ones try to occupy the spaces in between them. So there are very least number of spaces available in the entire lattice. The lattice is so closely packed that it would obviously be a solid at room temperature. It's going to be hard. It's going to have high properties such as melting point, such as boiling point, such as density. So since the packing is so tight and the arrangement is so regular, of course, all of these properties can be taken from ionic crystals. I hope that makes sense too.
Yes, sir.
Good. And let's clear it up and move to something we have been keeping pending for a very long time, macromolecules. Now, this is something that should have been done some time ago, but since the book keeps it pending, so we keep it pending too. So actually, the giant molecular crystals, or as the name says, macromolecules, the word macro itself means gigantic, giant, huge, all the meanings can be taken from the same word and it means the same thing exactly. They're not known as molecules. They are either known as crystals, lattices, or structures. Why? They're too big for the atom count to be counted, right? Water is a small molecule. Why? There are a total of three atoms, two of hydrogen, one of oxygen. That is not true for these examples. And this is actually graphite, both of the structures, this one as well as this one. This is graphite. So we really have three examples to go within this topic. Okay, let's start
Yes,
with
sir.
diamond first. Now, to begin with diamond, diamond has this kind of structure. Let me explain that every carbon atom is bonded to four other carbon atoms in case of diamond. So these carbon atoms are bonded to three other carbon atoms each, and the structure extends in all directions in three dimensions for the whole crystal. So much so that this extension depends upon the size of the diamond. If the size is small, there would be so many atoms of carbon bonded to four other carbon atoms in the entire structure. If the structure of that diamond or the whole crystal size is big, it's going to have even more atoms. So it's so difficult to count all the number of atoms. Yeah, we can count them, but it's difficult to express them in English words. Million, no. Billion, no. Trillion, no. Much more than that. Okay. For example, which means 12 grams of a diamond will easily contain 6.02 into 10 raised to the power 24 atoms in it, which is a big, huge number. Hence, we are using the term crystal, or we are using the term lattices, or we are using the term structure, but we are not using the term diamond molecule. The term diamond molecule is not correct. I hope that makes sense to you, right?
Yes.
Great. So each carbon atom is attached to four other carbon atoms. That's pretty simple. Since carbon has four electrons in its outermost shell, all four of them bond with a single covalent bond. So that's how the dot cross model goes. So we call this specific arrangement as tetrahedral. Tetra means four, hedral means head. It has four heads. Just explain the stuff, even if you don't know what tetrahedral actually means. And you can just simply look at the 3D diagram and use it. That is going to be good enough for your understanding at this level. So the atoms are arranged tetrahedrally. Diamond has a very high melting point because the bonding extends throughout the structure. It is very hard and it is used in cutting tools. So there are many properties given in this portion. The bonds are rigid. The structure is much more brittle than giant metallic lattices. So whenever you try to reshape it, it's going to break instead of getting into a new shape. There are no free electrons to move in diamond. Diamond is a typical non-metallic element. It does not conduct electricity. Let me tell you, diamond is also, because of its big, huge structure, insoluble in any kind of solvent. You cannot dissolve it in any solvent. All right. Now, since these properties are very much into one another in terms of sentences and words, it's better to take all the properties from the table below. Okay. So I'm going to go through the diagrams of graphite, and then I'm going to come back to this table and we're going to actually compare both of them, which is going to be easier for you rather than going with the whole paragraph. So when I am supposed to explain the shape of graphite, since I just explained a diamond with just one word, tetrahedral, I'm not going to explain it in the same way. Graphite is usually explained as hexagonal, and you might want to write it down, layered structure. Layered hexagonal or hexagonal layered. So if you look at this diagram, you'll understand that there are black balls representing carbon. And so there are 6 corners to this hexagon, and every corner is actually a carbon occupied. So it's much more like this one, right? Hexagon.
Yes,
But
sir.
the hexagons are present as layer over another layer, so on and so forth. So much so that if you look at any of these atoms, if I pick this atom, take a look, it's forming one covalent bond over here, second covalent bond over here, and third over here. If I pick this one out, one covalent bond over here, second over here, third over here. If I pick this one out, one over here, second over here, third over here. So all of these are actually making uh, finger covalent bonds, similarly like diamond. But what's unlike than diamond is that they are not making 4 bonds each, they're making 3 bonds each, which means every carbon, let's talk about this carbon atom, it would have one dot and cross over here, one dot and cross over here, one dot and cross over here, but it would have one electron, one dot remaining. And that one dot actually exists over here and they attract the structure over here. So we have weak interaction forces or weaker forces of attraction over here in between the layers. And in these weaker forces of attractions, we have many electrons free to move. And that's the 4th electron that is free to move in this case. Okay. So what happens is that we have a molecular structure. It's flat layers with linked hexagons. Each graphite layer is actually a 2-dimensional giant molecule. Within these layers, the carbon atoms are bonded to 3 other strongly covalently bonded to carbon atoms. And what's happening is that in between the layers, there are weaker forces of attraction. The layers are able to slide over one another very easily. That is why graphite feels slippery. It can be used as a lubricant. Lead pencils that we commonly use is actually graphite. When we write with a pencil, thin layers of graphite are left stuck to the paper. And actually, when we write with a pencil, there is a trail left over of graphite. That trail is commonly known as handwriting, right? When you write with a pencil, some of the graphite left stuck to the paper. That is known as handwriting, which for some people is really very good and easily readable. And for some people like me, handwriting is pathetic. Okay, I don't know which category you fall under, but I definitely fall under the second category. Okay, moving on. So the most distinctive property arises from the free electrons that are present in between the layers, and these electrons can move freely. They can carry the charge. So graphite, even when it's made from a non-metal carbon completely, right, it can conduct electricity. Now, let me compare both. Both diamond is made up of carbon atoms. Graphite is also made completely of carbon atoms. There is no other carbon atom, but this one is a conductor of electricity, and this one is an insulator for electricity. That's because carbon is bonded to four other carbon atoms in this case, and because here carbon is only bonded, my bad, to three other carbon atoms, and it has a free electron that can move in between the layers. I hope that makes sense, right?
Yes, sir.
Okay, good. The last one is silicon 4 oxide, which is not explained in the book, just the diagram is given for it. But let me explain, and you might want to draw it down. Every silicon atom is bonded to four oxygen atoms, and every oxygen atom is then bonded to another silicon atom, which is then bonded to more oxygen atoms. So silicon to four oxygen atoms and oxygen to two silicon atoms. That's how they're bonded. When we boil it down, we give it a formula of SiO2, which is silicon 4 oxide. We may also call it silica, a proper word, and actually sand composes of mostly silica. So all three of these words have been considered for the structure. Now let me tell you, this also has a tetrahedral structure. As soon as we use the word tetrahedral structure, you would immediately understand that the structure is similar to diamond. So if the structure is similar to diamond, the properties are also going to be similar to diamond. Since we are talking about properties, let's go to the bottom of the page number 83, and talk about the properties of diamond, graphite, and I'm going to also add silica to the list. Now, the first appearance, diamond is colorless, transparent, and sparkles in light. However, graphite is just dark gray and shiny solid. So is silica, they're all shiny. Diamond actually sparkles a lot, because of which it is a very precious stone on this planet. So much so it is used for decoration, and diamond rings are something that women are very fond of. I don't know why they are. Right? So moving on, next up is hardness. Diamond is the hardest natural substance. There are very strong covalent bonds extended throughout the structure in all three dimensions, so it's the hardest natural substance. So silica is also going to be hard. On the other hand, this one has a different structure. This one is soft, the layers can slide over one another, that's why it has a slippery feel. And it is used in pencils and lubricants. Why? Because it is soft, it can slide over. Diamond, however, being the hardest natural substance, is used in drill bits, saws, and cutters. Hardest natural substance means it can cut or scratch anything on the planet, but all the other things cannot cut or scratch it. So if you want to cut or scratch diamond, you need diamond to cut or scratch diamond. Since the hardest natural substance can only cut itself and everything else cannot scratch or cut it. So iron cannot cut it, no other element can cut it, diamond can. We're talking about just the natural substances, not the artificial one. We have many substances that are harder, even diamond, but those are artificially made. All right,
Yeah.
good.
Yes, sir.
Density. Diamond, since that is harder, it's going to be more dense than graphite. So graphite is less dense than diamond. So high density is also going to be a property of silica as well, since it has the
Sir,
same shape. All right, G.
could you tell the use for silica?
Yeah, I'm going to come to that. I am going to clear up the shapes as well as the uses as an addition to this table at the bottom of the table. Let me just cover the next line. I'll discuss shapes and I'll discuss uses at the bottom of it. Okay. So moving on, electrical conductivity. Diamond does not conduct electricity. There are no free electrons. No free electrons. And since graphite has free electrons, right? You may also write delocalized electrons, since that's a much better word. It can conduct electricity and it is used as electrodes, the electric rods that conduct electricity in electric motors, right? Since there are some uses written over here, here, and here, it's better that if I write the uses of silica, and it is used to make glass and watches, right? Glass is made up of sand or silica, simply speaking. Now that's astonishing for most of the students. Eh? Is glass made up of sand? Yes, glass is made up of sand. Okay. Apart from that, we need to discuss shape. This one is tetrahedral in shape, right? Remember the word. This one is layered hexagonal or hexagonal layered. You may use the term either way. And this one is also tetrahedral. Okay. This one is purely made out of carbon. This one is purely made out of carbon. This one is made out of silicon and oxygen. So SiO2 is the formula. So this is a big, huge uh, comparison table, this which includes the properties, reasoning to the properties, the shapes, what are they made of, and different uses along with it. Anything that you might be asked in past papers. And actually, yeah, some of this stuff has been discussed in past papers already. Okay, are you done writing?
Yes, sir, I'm done writing.
Good. Let's clear this all up. Let's move forward to the last page of the chapter. So silica shows the same physical properties in diamond. It is hard, it has high melting and boiling point. Sand and quartz are some examples of silica or silicon peroxide. We also call it silicon dioxide. The whole structure of silicon and oxygen atoms are bonded to held together throughout by the strong covalent bond, which is similar to diamond. Moving on to the last type, molecular crystals. Molecular crystals are actually simple molecules, but using the word crystal, it means that they exist in solid form. So we're not discussing the gases, we're not discussing the liquids, we're only discussing the solids over here. The examples to which are iodine and sulfur. Iodine has the formula of I2 and it exists in this form. Sulfur has usually the formula of S8 and it actually exists as octagonal shape, and it's better to draw it like this. Octagon, 8 corners. Every corner has a sulfur atom. So these are covalently bonded compounds. They exist as solid. They have low melting points really. In these crystals, the molecules of elements or compounds are held together by weak forces of attraction. So one II can attract another II by weak forces of attraction, or one of this ring can attract another of this ring. All right. This one can attract this one by weak forces of attraction. So these forces of attraction are actually broken down easily by heat. Molecules are then free to move, but unlike the particles in ionic crystals, they have no charge. Neither the liquid nor the solid forms of these substances conduct electricity. They are, and I'm going to add points to it, insoluble in water. Okay. Yeah, I forget solubility over there in the previous page. Okay, let's write this one and then I'm going to go back to the previous page first. When you're done writing, let me know.
Done, sir.
Good. I've got one little point on the previous page, so I'm going to go back and we're going to add solubility to it. So this one is insoluble in water. So is this one. So is this one. They're all insoluble. Actually, they're all insoluble in most of the solvents around the world, not just water. Sand is not soluble in water, so isn't graphite, so isn't diamond. And they're not even soluble in other solvents as well. All right. Done writing?
Yes.
Great. So, a quick comparison before we finish off the chapter. Um, Macromolecules have shared electrons, covalent structures, they have high melting and boiling points, atoms are linked together with strong covalent bonds. Metals, however, conduct heat and electricity because their structure contains delocalized or free electrons. The layers are able to slide over one another so they can bend and shape metals, malleable and ductile. Substances that are made up of simple molecules have low melting and boiling points. Even when they are solids, they're not able to conduct electricity. Now, compounds that are made up of ions are known as ionic compounds. They're usually arranged in a giant lattice with alternate positive and negative ions. They have high melting and boiling points due to very strong electrostatic forces of attraction. When they are dissolved in water or melted, they can conduct electricity because then the ions are free to move around and carry the current. And this finishes our chapter.